Okay, let's unpack this. Have you ever stopped to think about these huge structures holding just massive amounts of liquid? You know, the water for our homes, industrial chemicals, stuff like
Yeah.
that. These tanks and reservoirs, they're everywhere, sometimes right above us or nearby. But how do engineers actually make sure they're, well, safe, stable,
Yeah.
able to handle a full load, or even something like a big earthquake? It seems like a huge task.
It really is, and that's exactly the challenge we're diving into today. We've got this fascinating piece of research here. It's by Filip Tvrda and Manarova from the Slovak University of Technology, and they did a really deep dive into the static and modal analysis of a concrete tank filled with water. So our mission, really, is to understand how these advanced tools, like the finite element method, or FEM, how they help engineers predict how these vital structures behave, and, critically, avoid failure.
Right, so we're kind of pulling back the curtain on modern civil engineering, seeing how they use detailed analysis to guarantee safety and efficiency for these tanks. It's about understanding these invisible forces, isn't it? Making sure our infrastructure holds up. Okay, let's start with static analysis. Static sounds calm, maybe a bit dull, but it's about the constant forces, right? So when a tank's full of liquid, what's the main unchanging force engineers worry about?
Well, the absolute key factor is hydrostatic pressure. And what's really interesting is that it's not the same everywhere in the tank. It's not uniform. It actually increases quite dramatically with depth. You can almost picture it like a hydrostatic triangle on the tank wall. Zero pressure at the top surface, building up steadily to the maximum right at the very bottom. This paper really highlights how that pressure, plus the tank's own weight and the liquid's weight, how all that puts significant stress on the walls. It's not just theory. It's a powerful, measurable force.
Huh. So, like, if I imagine a tall glass of water, the bottom feels more pressure than the top.
Okay.
Now scale that up to a huge concrete tank, meters high, thousands of liters. The forces must be massive. But what does that constant pressure actually do to the tank itself, physically?
It causes this characteristic deformation. The engineers in the paper, they call it the elephant foot shape.
Elephant foot.
Yeah, basically the walls bulge out just slightly near the base. It's subtle but important. And this study, they used some pretty advanced software, NSYS Workbench and NSYS Mechanical APDL, to model this effect really carefully. But they didn't just, run the model and call it a day. They checked their computer results against established analytical calculations, sort of the traditional formulas, just to make absolutely sure their models were accurate. That validation is key.
Okay, and this is where it gets really interesting for the engineering side, right? The precision. They didn't just use one model. They compared different approaches within ANSYS. Something about linear versus quadratic elements for the tank shell. For listeners maybe not deep in finite element stuff, can you quickly break that down? Linear versus quadratic. Why does it matter for this elephant foot thing?
Sure, yeah. Think about drawing a curve. If you use linear elements, you're basically making the curve out of lots of tiny straight lines connected end to end. It's simpler, faster to calculate maybe, but it might not capture a smooth curve perfectly. Now, quadratic elements, they use actual mathematical curves to represent the shape and how it bends, like using flexible rulers instead of straight ones. So for something like that elephant foot bulge, which is a definite curve, quadratic elements are just inherently better at matching that shape and figuring out the stresses accurately. And they measured these horizontal bulges, like meter by meter up the tank's height. All 6 meters. They were really asking, which method gives us the truest picture?
And what did they find? Which one was more accurate? Because that's crucial for actually designing these things.
Exactly. So they used this measure called mean absolute percentage error, MAPE.
MEE.
Yeah, basically it tells you, on average, what percentage your model's prediction is off from the real or analytical value. Lower is better.
Got it.
And the results were, well, pretty clear. Using the quadratic elements, the method they called WB, QBD gave the most accurate results by far. The MAPE was just 0.67%.
Wow, less than 1% error.
Yeah, incredibly precise. And that number isn't just academic, it's vital for real-world design. It confirms that how you model it, even choosing linear or quadratic, makes a big difference in how trustworthy your predictions are. It means engineers can be much more confident, maybe use materials more efficiently, and spot potential weak points much earlier.
That level of accuracy is amazing. Okay, so that covers the steady forces. But tanks don't just sit there perfectly still, do they? The real world has wind, maybe ground tremors, even just vibrations from nearby traffic. So what happens when you factor in movement?
Vibration. Right, and that's where modal analysis comes into play. It's absolutely critical. Before engineers can figure out how a tank will react to dynamic loads, like, say, an earthquake hitting it, they first need to know its natural frequencies and mode shapes. Think of it like like a guitar string. Every structure has frequencies it naturally wants to vibrate at. Its preferred notes, sort of.
Yeah.
If something outside, like the wind or an earthquake, pushes it at exactly one of those natural frequencies, bam, you get resonance. And that leads to a really important question. Why is avoiding resonance just so critical?
Oh, yeah. Because resonance is, well, it's potentially disastrous. It's a nightmare scenario. We've all seen those videos, probably, like the Tacoma Narrows Bridge just tearing itself apart. For a huge water tank, resonance could mean total failure, liquid spilling everywhere, environmental damage, huge safety risks. It's not just a wobble.
Precisely. So the study took that idea and applied it. They compared the natural frequencies of the tank when it was empty versus when it was completely full of water. And what's really interesting, maybe even a bit counterintuitive, is how much the water changes things. For example, they found one mode shape for the empty tank vibrated naturally at 20.38 hertz. But fill that same tank with water, that frequency dropped way down to 12.00 hertz.
Wow, that's a big drop.
It is. It's a significant shift. The water doesn't just make it heavier, it changes the whole dynamic system, the mass distribution, the stiffness interaction. It completely alters how the structure behaves dynamically, like changing the tuning on that guitar string.
So it's not just if it vibrates, but how it vibrates too, right? These mode shapes.
Yeah.
They showed the first 4 ways the tank might vibrate. Can you describe what those might look like for us visualizing it?
Yeah, absolutely. So imagine the tank. The first mode might just be the whole tank kind of swaying back and forth gently, like a single unit. The second mode could be more complex, maybe the circular shape sort of ovals slightly, pushing in on 2 sides, bulging out on the others, like it's breathing.
Okay.
Then higher modes get more complex. Maybe the top twists one way while the bottom twists the other, or you get ripples up the side. These shapes aren't just, interesting pictures. They show engineers exactly where stresses will concentrate, or how the tank might buckle if it gets hit by forces at that specific frequency. It tells them where to potentially add reinforcement.
And importantly, did the different computer methods agree on these dynamic results too, like they did for the static part?
Yes, they did. And that's really good news for confidence in the models. Both NSYS Workbench and Mechanical APDL gave very similar results for the natural frequencies and the mode shapes. That consistency really validates the approach. It gives engineers strong reassurance that these tools can reliably predict dynamic behavior too.
Okay, so we've gone through the static pressure, the dynamic vibrations. Putting it all together, what does this really mean for, well, for us, the public? People who rely on these tanks without even thinking about it? It's about long-term safety, isn't it? Not just a quick calculation.
Absolutely. This kind of deep dive into static and modal analysis isn't just an academic exercise. It's the fundamental groundwork for designing safe, reliable structures that hold water, especially considering loads that change over time. And it goes beyond just the basics. This analysis is the starting point for much more complex assessments, things like how the tank would handle a major earthquake, or evaluating long-term issues like corrosion inside the concrete, or even looking for tiny potential cracks using fracture mechanics. It's about predicting the future, in a way.
Right. It really shows engineers aren't just guessing. They're using these incredibly powerful tools, backed up by solid checks, like that tiny 0.67% error we talked about, to make sure these essential tanks aren't just built, but are truly understood. Scientifically, predictively.
Exactly. Ultimately, if you choose the right computational approach, you can model the real behavior of the structure very efficiently and accurately, even before you build it. And that predictive power, it's an absolutely essential tool for designing and optimizing all sorts of similar systems. It guarantees reliability and safety, which is just becoming more and more critical as demands on our infrastructure grow.
What a fascinating look into this hidden world of structural engineering. We've learned that even something that seems simple, like a concrete tank, needs incredible precision. Both static and dynamic analysis are key to making sure it's safe for the long haul. From that elephant foot bulge due to water pressure to understanding vibration frequencies to avoid disaster, it's really clear that computational modeling is the quiet hero behind so much of our reliable infrastructure.
It really is.
Yeah.
So next time you pass a water tower, or maybe a big industrial tank, take a second to think about that complex dance of forces and vibrations it's constantly dealing with. And then here's something to think about. If just filling a tank with water significantly lowers its natural frequencies, changing how it might react to, say, an earthquake, what other subtle changes in a structure's environment, or maybe its contents, could be silently altering its fundamental stability and safety? Things just waiting for a deeper analysis to uncover them.
That is definitely something to ponder as you go about your day. A great reminder of the engineering all around us. Thanks for joining us on this deep dive.